Hello everyone, this is my circuit and is designed to capture the heartbeat sounds through a microphone and process the signal using a multi-stage amplifier circuit, ultimately driving a speaker to broadcast the song. We will go through each stage of the circuit step by step, explain its function, show real measurement result, and link all observation to the circuit design. So the system has four main stages. Stage 1 is a preamplifier which boosts the raw signal. Stage 2, which is a high-pass filter, remove body motion noise. Stage 3, low-pass filter, which eliminate high-frequency interference. And Stage 4, audio amplifier, which drives the speaker. I will now go more in deep into the different stages. In stage 1, the ICTL072, which is a low noise dual input op-amp, is used to boost the weak microphone signal. The output of the microphone goes through capacitor C1, which is 10 microfarad compelling capacitor that blocks out DC bias voltage and only allows AC bias voltage to pass through the op-amp. This is essential to prevent any unwanted DC offset from affecting the op-amp input. Then there are two 10 kilo ohms resistors, R5 and R6, connected in series between the 9-volt supply and ground. Together they form a voltage divider producing a stable midpoint voltage of 4.5 volt, exactly half the supply voltage. This 4.5 volt is used to bias the non-inverting input of the op-amp in a single supply configuration. The presence of the resistor R2 and R3 and capacitor C2 and C3 forms a band-pass filter. It has a gain of 23, which is derived from the formula AV equal to 1 plus R2 divided by R3. This band-pass filter only allows a desired range of frequency, specifically those of the heard sound, to pass through the amplifier, while unwanted noise and irrelevant frequency are filtered out. According to my calculation, the range of frequency allowed are 16 Hz to 1600 Hz. Lastly, the 10 microfarad capacitor C4 acts as a compelling capacitor for the output of the op-amp. It blocks DC while allowing AC heartbeat audio signal to pass through. This prevents DC bias from one stage from interfering with the next stage or the speaker. Based on this table for the amplifier in stage 1, we can see as frequency increases, the gain will also increases until its maximum of 23 as was calculated earlier on. Its frequency will be at 100 Hz, and frequency higher than 100 Hz will cause the gain to drop. Gain at 23 will be equivalent to around 27 dB. So based on the frequency response curve, the minus 3 dB line will be at 27 minus 3, which is 24 dB. So low frequency is at 16 Hz, while high frequency is at 1200 Hz. Therefore, the bandwidth will be 1.2K minus 16 Hz, which get the result as 1184 Hz. As the op-amp is biased into a single supply configuration, the negative side of the sine wave will be cut. But the voltage divider also acts as a level shifter, shifting the entire waveform up. The waveform is shifted up until the midpoint of the sine wave equals to 4.5 volt. This ensures that the whole waveform is above the negative edge and the sine wave will be visible. To set up stage 1, first turn on the power supply DC source to 9 volt and connect it to the circuit. The function generator frequency needs to set to sine wave 1 kHz at 200 mV peak to peak. Then we connect with channel 1 probe of the oscilloscope to the function generator. By placing the probe of channel 1 to TP1, we can see that the output voltage is at 200 mV peak to peak. Pin TP1 to channel 1, and by placing the probe of channel 2 at TP2, we can get an output voltage of 3.4 volt. For stage 2, it uses the same IC as in stage 1, a TL072, but in this case, it is a negative feedback loop amplifier. The op-amp feeds a portion of the output signal back to the inverting input, where a 180-degree phase inversion occurs. The IC has an adjustable gain which is controlled by the trimmer P1. This adjustable gain will make the op-amp function as a linear amplifier. This stabilizes the gain and prevents the amplifier from saturating or distorting the input. Pin 5 of the op-amp is connected to a voltage divider consisting of two 10 kΩ resistors which are R9 and R10. This creates a visual ground where the op-amp operates at 4.5 volts. Without this, the op-amp would try to amplify a signal centered around 0 volt, which doesn't exist in a single supply system, and the output would be clipped near 0 volt. Stage 2 is key in the circuit as it filters out high frequency noise and keeps only the low frequency component of the heartbeat signal, which helps to clean up the signal before it's sent to the next stage. To set up stage 2, we will put the output of TP2 at channel 1 and all frequency as well as power supply to be left untouched. We will place channel 2, browse off the oscilloscope to TP3, then we can get output voltage of nearly 6 volt. By turning the trimmer, we can see how it affects the output waveform. As I adjust trimmer, the waveform will be amplified and at some point, it will become saturated and cut off. Now for stage 3, before input is delivered to the op-amp, it first goes through capacitor C5. It lets the heartbeat signal through but block unwanted DC voltage, ensuring a clean center signal is sent for filtering. Then the signal passes through a voltage divider of resistor R11 and R12, which also serve a secondary purpose as a level shifter to prevent clipping of the output. The output is then sent to IC2A. It is configured as a second-order silent-key low-pass filter, consisting of two low-pass RC networks. Combined with the op-amp, it creates a sharper frequency cutoff compared to a first-order filter. This setup effectively removes high-frequency noise while preserving the low-frequency heartbeat signal. Capacitor C8 is connected to the output of the filter. It serves the same purpose as capacitor C5, blocking out DC voltage in the output before sending it to the stage 4. Stage 3 is important as it cleans up the signal and prevents unwanted noise from being sent out and ensures that only the clean filter signal gets amplified in the next stage. This removes the junk and highlights what really matters in this biomedical signal processing system. As the lower frequency that can be passed through is 0 Hz, the bandwidth will be equal to the cutoff frequency which given by this equation. Based on this table, we can conclude that when frequency is below 100 Hz, the filter is at unity gain. But once the frequency is above 100 Hz, gain and output voltage will begin to drop. So, based on the frequency response curve, the -3 dB line will be at 0 -3, which is -3 dB. The high frequency will be at 1.2 kHz, hence the bandwidth will be 1.2 kHz minus 0 equal to 1.2 kHz. By keeping TP3 at channel 1 and all backdrop untouched, we can place channel 2 probes of the oscilloscope to TP4, and there we get a filter output voltage of 4 volt. The output waveform at TP4 will be determined by the output at TP3. Hence, by adjusting the trimmer at stage 2, it can control output at TP4. As I mentioned earlier on, when frequency is below 100 Hz, the amplifier will be at unity gain, which means it has gain 1, which will be equal to the input voltage. However, in this case, unity gain is not applicable as frequency is set to 400 Hz. So there is a drop output voltage from TP3 to TP4. So final output is maximum as sine wave attained without being saturated. Lastly, for stage 4, a LM386N1 is used. It is low voltage audio power amplifier. It takes a low level filter signal from stage 3 and boosts both the voltage and current so the heartbeat sound can be clearly heard. LM386N1 also has a built-in gain so no additional external components are required. Capacitor C15 is used to suppress high frequency noise, helping to smooth out the output waveform. This improves output signal stability and improves the sound quality and makes the heartbeat sound clearer. Capacitor C13 is a compounding capacitor that filters out DC voltage and allows AC voltage to pass. Then there is a trimmer P2 which controls the amplitude of the signal going into LM386N1. The input will first go through trimmer P2 where pin E has full amplitude while pin A and S has zero amplitude of the input waveform. To set up stage 4, we will do the same as earlier by keeping TP4 at channel 1 and all patch up untouched. We will then place channel 2 probe of the oscilloscope to TP5, then we get output voltage of around 7 volt. By adjusting trimmer P2, we can control output at TP5. Final output is maximum as sine wave attained without being saturated.